Good morning, good afternoon, and good evening, everyone, and welcome to this Inside Scientific webinar titled Mapping Heterogeneous Interfaces Using Single-Entity Electrochemical Microspectroscopy. I'm Liam Sanyo from the events team here at Scientist.com, and I'll be your host today. This webinar has been sponsored by Harvard Bioscience and its affiliate HECA, so a big thanks to them for helping to make this webinar possible. We're very fortunate to be joined by Dr. Venkateshkumar Prabhakaran, who's a senior chemical engineer at Pacific Northwest National Laboratory. Today, Venky will describe the development of scanning electrochemical microspectroscopy and its application to characterize heterogeneous electrified interfaces. All right, I'm very pleased to welcome Venky. All right, thanks so much for joining us today.
All right, thank you. Hello, my name is Venkateshkumar Prabhakaran. I go by Venky. I am a senior chemical engineer at Pacific Northwest National Lab. I also have a joint appointment as an adjunct assistant professor in the chemical engineering department of Washington State University. First of all, I also like to thank Frank from HECA, Harvard Bioscience, and also the Liam and Jamie from Inside Scientific for inviting me to talk about our latest development on mapping heterogeneous interfaces using single entity electrochemical microspectroscopy. So with that, let's dive into the seminar. The simplified electrochemical interface shown in this figure, the leftmost, is an integral part of any electrochemical technology, likewise in batteries or fuel cells or anything. However, in reality, these electrochemical interfaces used or exist in many applications is much more complex due to the presence of different type of ionic mixtures that stems from cations, anions, or neutral or solvent molecules, and also a different mode of operations that taking place, everything in a single operating electrode-electrolyte interfaces. So the critical knowledge gap still exists on understanding how one can selectively control all these complex interfacial processes that involves the transfer of charged or uncharged species in presence of various ions or phases under the electric field. So addressing this knowledge gap is also very relevant to the mission of US Department of Energy, Basic Energy Science, also my group at PNNL. So the main objective of our group at PNNL is to achieve the mechanistic understanding of this ionic or charge transfer dynamics that takes place at the operating interfaces using advanced electrode preparation technique like ion soft landing, and employ nano-electrochemical techniques to characterize the interfaces to elucidate the surface chemistry during the reaction. Today, I will be focusing more on talking about different modalities of nano-electrochemical characterization techniques, and I will leave out details about the ion soft landing. But in case if you want to know about the techniques, you can find it online on my group. So the conventional electrochemical techniques that exist for over a century or more usually consist of something looks like this. So it has a bulk electrolyte solution, which has a reference counter electrode, and also the working electrode is your sample surface. You apply electric field to the working electrode and to monitor the reaction kinetics where the reactant O can go or gain an electron or lose an electron to form a product. So these conventional electrochemical techniques has been combined with many spectroscopy techniques to understand the interfacial processes in bulk. However, the most of the techniques relies on exposing the entire surface to the electrolyte solution and then monitor the interfacial reaction at the high spatial resolution. But it lacks this localized surface-dependent activity. What that means is that some of the electrodes used in many applications, for example, in batteries or electrode deposition, the amount of ion that accumulate on the surface is not very uniform, and it really depends on the different heterogeneities on the surface, like cracks or pit holes or anything. If you use a bulk electrochemical technique, it gives you an entire response at the same time that leaves out the details, surface-dependent details. So understanding this localized surface-dependent mapping is a key to enable the fundamental understanding of the interfaces. So to that end, so I'm going to introduce one of the techniques that exists in the world of single-entity nanoelectrochemistry. So the single-entity nanoelectrochemistry is started most likely from, at least to my best of my ability, started when the scanning electrochemical microscopy technique exists, wherein they used the microelectrode dipped into the solution and try to understand how the redox molecules reacts between the surface and the microelectrode that nears to it. So by monitoring the number of times the redox molecule going like a ping pong fashion, so you can estimate the surface mapping and how the activity changes across the surface. There are various applications that stemmed from this SECM that still exist and used in many groups and in many applications. But one of the key disadvantage, I wouldn't say the disadvantage, but one of the key the drawback is that we need to expose the entire surface again to it. And this is problematic for some of the applications, such as in catalysis or corrosion, wherein as soon as you expose the surface to the electrode, the reaction starts. And by the time you go from one location to the other location, your surface may be forming a more thicker oxide layer, or otherwise it leads to a loss of information. So there are other techniques that developed after the SECM that improved upon is an SICM, wherein it uses a similar concept, but instead of using a microelectrode, we use the capillary, the finely pulled capillary that either forms a droplet or meniscus. Something looks like this and lands on the surface, wherein you basically can insert the counter electrode on one end and make your surface as a working electrode. And by measuring the current between these two electrodes, one can understand the various diffusion kinetics or other steps. And there are other versions of the SICM where the surface is being exposed to an entire electrolyte solution, but still the diffusion or mass transfer is limited through this nano or tiplates. The improvement over the SICM is developed by the Professor Anwin group, wherein basically instead of a single barrel capillary, the theta capillary is used, wherein you take a theta capillary and pull it to the fine length and insert these two electrodes. One act as a reference, other act as a counter, or you can both these can act as a pseudo counter or reference in a way the configure you want, and it still forms a tiny meniscus at the end, and then you can land it on the surface, and it makes a perfect 3 electrode traditional cell. But only thing is that you only selectively exposing the tiny electrolyte area that formed by the meniscus when you land on the surface. So all this mode of electrochemical imaging using the single entity nanochemistry has been has enabled the localized mapping and applied in various fields like energy, corrosion, biology, or medicine, on drug delivery system, etc. And recently there is an excellent review article published by the Professor Patrick Anwin's group. I would like, if anyone interested in it, take a look at it. It's very interesting to read. That summarizes almost every possible techniques, very exhaustive, very thorough review. So what I'm going to talk about today is the SECM. It's basically the nanopipette-based technique that uses a theta capillary as a probe. So like I said before, so you can use the theta capillary and insert the 2 electrodes, and your diameter of your tip is basically an approximate size of your electrochemical cell junction that you are going to form when you land on the surface. There are various techniques that is being used. to control how you can land on the surface, because unlike the other techniques like a microelectrode or the SICM technique, it is important to maintain the tip and surface distance so that your droplet is more stable or well defined throughout the measurement. So the one interesting, the one more conventional approach of landing the SECM tip on the surface is to monitor the current between the two barrels. That is going to create some type of an approach curve, and as soon as the current reaches the certain point, or as soon as the tip lands on the surface, it will squeeze the droplet, and then the current decreases, and you can define how much you can correlate the squeeze in the or the decrease in the current to the where you wanted to stop on the surface, and that will make as an exact can be used to maintain a constant distance between the tip and the surface throughout the measurement when you land on it. So you can land on these and you can scan through or raster through. You can do hop in and hop off mode to go between two places, or you can continuously make a series of pixels, later scan, and once you land on the surface, you can essentially do any type of electrochemical techniques, where cyclic voltammetry or electrochemical impedance spectroscopy, or all AC and DC technique as well as I know, but each technique has an advantage and disadvantage, but that I'm going to talk about today in the two different applications. But having said that, so this is the working principle of the SECM tip on it. So I'm going to show some of the video that I'm trying to play. Yes. So basically, this is how the SECM tip works in action. So you land on a surface, make a measurement, and then retract on a surface. And you can do raster around the surface to make a line scan or go to a any local points. But one still, it's a disadvantage for certain application, but not all the other application, particularly in corrosion, where we have to use a salt solution in the tip. That prevents that usually it creates an salt precipitate around the tip that affects some of the measurement, like you are seeing it here. And there are some ways to control the salt precipitate formation. So in our lab, we try to use or maintain the relative humidity around the tip so that the precipitate formation can be controlled. So we basically use a soaked or sponge paper around the sample that creates kind of like a local humidity or a relatively high humidity, or the way you make the tip also sometimes helps, where after you pull the tip, if you coat with some hydrophobic coating like a silane, it helps to minimize a salt precipitate formation. So these are some of the disadvantage, or still we need to work on it. There are other methods that recently coined by the Professor Janine Maserol from McGill University, where the Professor Maserol basically used a thin oil layer on the surface and land the SECM tip on it. And because of this, the oil layer prevents the evaporation of electrolyte layer, so you could avoid a salt precipitate formation. And it's a very excellent alternative method to control the salt precipitation when you scan over the entire surface. One disadvantage is that it may be useful for an application where the oil do not react with the surface, particularly in the case of like a corrosion. Some of the surfaces are dull or less reactive, but it may not be applicable directly for say like in catalysis, where the oil could essentially break down your organic molecules. So having said that, I'm going to talk about the application of an SECCM in two fields today. One is the electrocatalysis, other one is the electrochemical corrosion. In electrocatalysis, in our lab, we combine the SECCM with several microspectroscopy tool and calling it as an ISCCMS platform, which enables the localized mapping of electrochemical activity in addition to the spectroscopy as well. So the main research objective is to use this SECCM platform to study the reactive oxygen species that generates in the oxygen reduction catalysis. In our case, we demonstrated this platform for monitoring the ORR activity or the oxygen generation of reactive oxygen species at tantalum titanium oxide. So basically, in this approach or in this research, we perform the SECCM scan in situ and also coupled with an ex situ technique to establish the reliability of the technique, and so that we can establish as a platform to monitor these free radical generation. So how we combined is basically use the SECCM platform on a Hacker platform that we purchased, and instead of using the opaque electrode, we used the ITO electrode, and we constructed the inverted microscopy setup under the platform or under the surface, so that we can focus the objective lens directly to the tip end. So this type of inverted microscope works when you have your electrode is more transparent rather than the opaque. So we have to use this indium tin oxide like electrode, and we sprinkled or we spreaded the electrocatalytic catalyst, in this case titanium. Tantalum titanium oxide on a indium tin electrode, and then look at how the ORR land on the each particle, and then look at how the ORR activity changes as a function of generation of free radicals. So here is the view of the setup we have. The leftmost is the real view, but what I was would like to draw attention is that so we use a tip like this on the right hand side, but when you see the tip from the underneath, so you can see a tiny spot here, and since the microscope or objective can be able to focus on the tip, essentially you can do any type of microscopy based on what type of laser or light source you are using and how you are collecting this setup. So in our lab, we use a modular system so that we can switch between an absorbance, fluorescence, and recently we also are constructing a Raman spectroscopy along this platform. And the another point I would like to mention is that the SECCM tip is combined with the shear force microscopy, which is basically a tube plate that you are seeing it here, that helps to use this vibration of this tip as another mode to land on the surface. But we are it is good in some cases where you do not get a very good current response, and or when you wanted to use a very small tip, so the shear force microscopy comes into hand to achieve that. So using this ISCCMS platform, we initially worked towards understanding the spectroscopy signature of a polyoxometallate, which is in what we colloquially call it as a POM, which is a metal oxide cluster, which looks something like this. But the interesting property of the polyoxometallate is that it has a multi-electron redox activity, as you can see in this cyclic voltammetric figure. And understanding how this multi-electron redox activity changes when when the POM ions are near to the surface or on the electrode as a function of its distribution is key in many energy applications. For example, if the POM act as an isolated molecule, we usually observe a high reactivity. But when the POM aggregates near the electrode and forms some kind of like a very nice snowflakey like structures here, your activity tends to reduce because of an impedance or impedance in the charge transfer process during the redox reaction. But another interesting property is that it has a very peculiar UV-Vis or a particular UV-Vis spectroscopic signature. So we can coat the surface or the ITO surface with a POM molecule and was able to measure the spectroscopic signature at a different potential range. In this case, it basically we were able to see a distinct signature around an UV region around 1 and also around a high visible region around like in between like 650 to 700 wavelength region. And we also show that it the response quite dramatically changes when you swap from a 0 to minus 1 volt. That means it goes to a higher oxidation state. So it forms kind of like a blue color, which is also a well-known phenomena. That's why the peak around like 600 to 700 increases when you increase the potential. So this gives a confirmation of setup works. Then we use this setup basically to understand an fuel cell oxygen reduction reaction activity. So this is a basic function of the fuel cell, wherein you have an anode and cathode, wherein oxygen is pumped into the cathode side of it, and hydrogen is pumped into the anode side of it, and hydrogen oxidizes to form a proton that combines with oxygen that forms along with the 4 electrons to water. But usually the formation of or the reduction of oxygen to water is not a straightforward process. It involves many intermediate steps. And one of the rate limiting intermediate step that is being identified is the generation of this hydrogen peroxide, H2O2 SN. And whenever there is a generation of hydrogen peroxide during the oxygen reduction happens, this peroxide can further decomposes in presence of metal ion impurities around in the electrode area and forms these hydroxy radicals. And these hydroxyl radicals are very active, and it degrades the electrolyte structure and also the membranes that eventually leads to catastrophic collapse of the fuel cell itself. So understanding the redox reactive oxygen species at the molecular or catalytic level is a key to control or establish the different electrode design or geometry of it. And so far, there are plenty of other advanced characterization tools like an electron paramagnetic resonance spectroscopy has been used to monitor this redox the ROS generation. However, it does not offer the spatial resolution. So that means you would not know how the heterogeneity of an electrode affects the ROS generation. So here we are trying to address that. So previously, during my undergraduate research under Professor Vijay Ramani, I developed a technique called an in situ fluorescence spectroscopy using a dye called 6-carboxyfluorescein, which is sensitive to the hydroxy radical. So we are able to incorporate this dye into the fuel cell in the membrane part of a membrane electrode assembly and insert the fluorescent probe locally so that you can actually monitor how the RO is being generated just by monitoring the fluorescent decay over time. So here is where our showing basically is that there is a two type of electrodes we are comparing, or the catalyst we are comparing. One has the platinum carbon on a carbon support, where the carbon is known to form a higher amount of hydrogen peroxide. So the redox ROS, or fluorescent decay, is increased compared to another experiment where we use non-carbon based titanium, or the ruthenium oxide based support, where the hydrogen peroxide or reactive oxygen species is very less. So considering that we are able to develop this 6-carboxy fluorescing based probe that work with the bulk fuel cell, we employed this fluorescent dye into an SCCM setup. So basically, what we did is that we created an electrode surface wherein we formed naphthion is an electrolyte membrane combined with the 6-carboxy fluorescent dye coated on the surface, along with the overall catalyst particle, and then we basically filled the electrolyte with the oxygen purged electrolyte, and flow the oxygen around the SCCM tip, and monitor the fluorescence of 6-carboxy fluorescein as you raster around or land the tip on a different particles on the electrode surface. So here is the overall activity itself, that we wanted to make sure that overall reaction happens first. So basically, we are trying to compare with the XO2 overall reactivity of that particular catalyst, where the onset is around like 0.6. It clearly shows a typical overall polarization plot. And when we compare with the in situ overall voltammetry that obtained using the SCCM tip, we are able to clearly get these similar trend in the overall activity. But obviously there was a shift in the potential and also the reduced current, because of an reference electrode we are using is just an EG wire, as opposed to another type of very good reference electrode or RHA electrode used in the bulk experiment. But the key aspect of it is that the overall trend is same. That means the overall reaction occurs on the particle when we land on the tip. So when we are doing this overall measurement, we are able to simultaneously collect the fluorescent signal, and we compared the fluorescent decay of an electrolyte solution with and without catalyst. The one on the left basically shows that there is a fluorescent decay in presence of electrolyte that contains the 5% hydrogen peroxide. So we artificially introduce hydrogen peroxide, but no catalyst. And to see that how stable the fluorescent dye molecule is itself, whether it is being responded. And you can see that when you introduce the peroxide into it, though there is an increase in the fluorescent decay, that is probably due to an generation of free radicals that formed out of the hydrogen peroxide. In presence of the catalyst, a similar trend happens, wherein when you have a catalyst layer, but without the instead of oxygen purged electrolyte, we use the argon saturated electrolyte, wherein the fluorescent decay is minimum. But as soon as you start to use oxygen saturated electrolyte, we have an increase in the decay activity. So there's this increase in the fluorescent activity. Decay represents the additional or the ROS, the reactive oxygen species generated on the particle. So this, as you can see here, that there is plenty of work still needs to be done to stabilize the response, even without when you don't have this leaching hydrogen peroxide, and we are working to improve the robustness and stability of this type of fluorescent probe. So the another application of SCCM ICCM platform is that wherein we apply into study some biological process, particularly in the onion cells, wherein we wanted to poke into the onion cell and understand the spectroscopic response. Herein, we basically, instead of a fluorescence spectroscopy, we use the hyperspectral detector, wherein it measures the absorbance of absorbance signal of a certain region of the surface or the sample, and we can SCCM technique allows to land on each part of the onion cell, and then able to understand how the ion conductance or other electroactive species they react, or you can actually do any type of electrochemical reaction and then monitor the signal. So this is a quick example, but we are still working towards to make a good application using the hyperspectral imaging, and it probably will be also applicable to study biocatalytic or biomimicking catalysis in future. So as a conclusion of the first part of my talk is about we established that SCCM platform is very useful to study and spectroelectrochemical signatures of redox and reactives. The reactive species on an electrode, and it allows to measure an very intermediates like an reactive oxygen species generation, which is applicable to designing a high performance or a catalyst in future. The another application I want to cover with the limited time I have is on the electrochemical corrosion technique or application, wherein we combine the scanning electrochemical cell microscopy with impedance spectroscopy. So why impedance? So the electrochemical impedance spectroscopy is a unique AC-based technique that employed as in an electrochemical method. So instead of applying a linear voltage or the input, the sinusoidal input excitation is applied to an electrode, and the response current is monitored or measured. And by analyzing the phase shift and the resistance that comes out of this sinusoidal input and output, you can construct the Nyquist plot, something look like this, wherein the x-axis is real impedance and y-axis is the imaginary impedance, and the shape of the curve or the different regions of the curve represents the different key processes that exist in the electrochemical interfaces. For example, in the first lower or high frequency region, what we call it, that represents kinetic part of it, and the mass transfer control part of it comes with the low frequency region on it. And there are many methods developed over the past few decades to analyze the EAS data. So the combining the EAS technique with SCCM gives you a powerful approach, not only to study the typical current voltage response, but also understand all the other interfacial resistive components that exist during the applications or the activities in corrosion, batteries, or any biological systems. The another key extension of electrochemical impedance spectroscopy is an ability to do a distribution of relaxation time analysis, which basically are represented by these two figures. So usually in the EAS data, the response of the EAS data can be fitted into the equivalent circuit like this, that each component can be represented by a single peak or the time-dependent activity. However, when we do a real the distribution of relaxation time analysis based on a bias and reach or any other analysis method under the tools like PYDRT tools, or that's basically on a free Python platform, you can also generate a time-dependent distribution of each time constant. That means instead of having a one peak, you can get the distribution of the resistive values, and the shape of this tells you more about the processes, how the particular event, for example, charge transfer relaxes over time. And this has been a key finding is key application in many electrochemical technology, but particularly in batteries, wherein it's very useful to characterize the interfacial components or all the other diffusion components, like I showed in this figure, as a function of a time. So it's extremely valuable to delineate the complex intertwined interfacial process especially when you are able to collect at the single entity level during the reaction. So we use it, we combine this SCCM with the scanning electrochemical impedance microscopy. Basically, after you land the tip, you can collect the basic electrochemical impedance spectrum and then convert that into the distribution of time, relaxation time analysis, something I'm showing it here. But one of the key thing I want to mention is that it's very important to maintain the stability of the tip. That means any precipitate formation at the tip end that will affect the distribution of it and give you an unrealistic curve. So we started with a lower tip size, but eventually we found out that the tip size needs to be more, like in 8 to 10 microns. That basically forms an high. The larger contact area and minimize the evaporation rate or precipitate formation of it. And also the soaked method also works to maintain the humidity of it. So after we combine the SCCM with the EIS and DRT analysis, we apply to study the corrosion. So here is a typical the plots you can get at each point on the surface. So you can get the Nyquist plot, or you can get the Bode impedance or Bode phase plot distribution. And as soon after you get this type of basic EIS response, you can use the algorithm using Python DRT tools or other tools to convert that into the DRT plots on it. And you can analyze the DRT plot to establish the different components of it. So I will quickly show how the EIS data is after we combine the SCCM with the EIS, how we use it for the corrosion activity on a different surfaces. First, we started with the magnesium single crystal because we wanted to compare the responses of SCCM tip in a bulk, and also compare with the response with the SCCM or tip that is measured locally. So here is an open circuit potential. Basically, one thing we notice is that even though the potential ranges are same, when you do the SCCM measurement to measure the open circuit potential, it quickly achieves the steady state far faster than the bulk experiment. Is probably because it would take much less time to attain a equilibrium condition as soon as the tip lands on the surface compared to a macro scale environment. And we found out that by maintaining the other experimental parameter constant, you can typically maintain the OCP over time or a different reaction, so that you are seeing it here across the different points on a single crystal surface. The response is same. Next, the TEFL polarization is another characterization that typically used in corrosion to characterize the corrosion behavior of the surface. Interestingly, when we compare the corrosion TEFL polarization with a bulk SCCM, showed minor variations in the type of the curve where it lands, the shape of the curve as well on the ECOR points. But overall, we attributed that even though we use a magnesium single crystal, there is still chance that there is an uneven distribution of a surface oxidation could take place that could result in these minor variations of it within the plus or minus 100 millivolt. But overall, the shape of the curve is very similar to the bulk, and it's been constant over the different points on the surface. So the next, the electrochemical impedance spectroscopy, where we did it on a the similar curve, wherein it also showed a very similar response. But here, what we also observed is that there is an increase in the resistive component when you use ACCCM tip, is probably due to an partial droplet evaporation, and so the quick measurement is absolutely needed at this when we do the EIS measurement. That means you cannot do an entire frequencies, but you have to select the frequencies. After the EAS, we did the DRT analysis, and it also revealed a very reduced number of characteristic peaks in the ACCCM data compared to the bulk, which usually means that the bulk could have it's an ensemble response. So you have many different elements that can play together that forms the many different peaks, wherein ACCCM is a very localized response that leads to a very small number of DRT peaks. But essentially, you can get all this, the peaks about the charge transfer resistance related to an oxide layer formation. This are very useful for corrosion application. Then once we established on a single magnesium single crystal, we were applied this technique to raster across two different metal, like a magnesium and steel metal joint. As you can go shown in this figure. So you go from one side of a joint to the other side to look at how the local variations affects the different TEFL and EAS behavior. And basically, you can get the EAS behavior near the joint, which is very crucial information because what we are seeing here is that the magnesium side shows a more time-dependent activity compared to a steel side. So that indicates that the magnesium corrosion is much more complex reaction compared to the steel side as well. And here is, and you can also raster around instead of a point to get an image of it. So here is an example where we did the corrosion ECOR and OCP mapping across the interface, where you can clearly see a transition from a OCP or potential from a steel to magnesium side, and how the potential distribution changes near the interfaces, and which we found out that the near the interfaces is more corrosive due to a galvanic coupling process. But the EAS distribution is not very well defined. It's probably due to limited spatial resolution. We may need to have more statistics of the data, but here we haven't found any significant variations or distinction near the interfaces. But the so far I have talked about how the ACCCIM can be used for the metal joints, but you can also apply to study grain boundaries of metals. That is very important for corrosion application. Whenever, for example, whenever there is an alloy formation occurs, or when you prepare the corrosion metal for the alloys, the different islands that forms and precipitate that forms on the surface exhibits the different corrosion behavior. Sometimes it can also act as an starting point for the corrosion. So as a conclusion of today's talk, so we successfully integrated the SECCM with the optical and impedance spectroscopy that enables to characterize the electrochemical activity on a side-by-side basis. And the precipitation issue is a key issue is still existing, and designing some microhumidity channel may eliminate some of this issue. And integrating with an upright spectroscopy technique with Raman would also enable more structural function relationship measurement for opaque surface, because so far we have done only for the indium tin oxide, which is transparent surface. With that, note, I would like to conclude my talk by acknowledging my amazing team at PNNL, both in separations and corrosion studies I was talking about today, and also our funding agencies from US Department of Energy, and also on internal funding and industries, and also last but not least, the Insight Scientific and also the HECA for inviting me and hosting this webinar to talk about our exciting science in this field. And with this, I would like to get your attention. And thank you very much for listening to my talk. So this is the picture I'm showing where I am located, Energy Science Building at Central. If you have visiting the PNNL, inform me, we can arrange a lab tour. I also look for many interesting interns available in my lab as well. So I am happy to take any questions and happy to answer to best of my ability.
Excellent. Well, thanks so much, Venky, for a great presentation. So yeah, move on to the first question here. Venky, how long does it take to make each measurement?
It typically varies, depends on the type of measurement you do on each after you land the tip. For example, if you want to do a simple voltage or current measurement, it typically takes a couple of hours for the 100 by 100 micron area. But if you want to do EIS or TAFL or entire sweep, usually takes like 6 hours or so. So it varies around that, but the important point is also to keep the tip not dried completely. So we will usually play around with the tip diameter and how fast it dries to maintain the stability of the tip throughout the times.
Fantastic. Yeah, great answer. All right, next one here. Can the scanning EIS or scanning electrochemical studies be performed at a high temperature, like in the range of 280 Celsius to 315 Celsius, and in an acidic environment?
It's an excellent question, and it's one of the questions we, as a community, we always ask. In generally, no. To best of my knowledge, no one has tried to use ACCCM at high temperature, but however, it is possible to do the high temperature if you are working with an electrolyte that do not evaporate at that temperature. I believe in aqueous electrolyte, it's not quite possible because you typically have a high evaporation rate. But I would say that in the non-aqueous electrolyte, if the electrolyte is stable, one could try in a controlled environment. But for those applications, you may need to put the entire setup inside the nitrogen environment or other environment to keep the tip stable. Otherwise, you will have a lot of evaporation that creates a bubble and blocks the measurement.
Perfect. Yeah, great answer. All right, in your SECCM work for corrosion imaging, what is the common tip diameter that you've worked with? And what challenges would you expect if somebody uses nano-sized pipette tips in the SECCIM experiments?
In regular SECCM experiment, in our group, we used tip diameter all the way from 200 nanometers to 10 microns. But again, it depends on the application. For a catalysis application, one would need a smaller diameter, or less than a micron like diameter. And typically we use an acidic solution and that do not evaporate or do not have a salt, so it does not evaporate. So it's easier to use a small diameter tip. But in the corrosion application, like I mentioned before, if you use a salt solution, it evaporates quickly. If you use a small tip, so you need to go for a little bit larger diameter tube, typically 3 to 7 micron range. And I think the second question is in case of SECCIM impedance spectroscopy, it is also very sensitive to the tip diameter because the tip diameter also act as another element in the impedance. That one of the reason if you use a small tip diameter, your impedance values are usually higher. We also are a little bit optimized on that end, and typically found out that if we use above 5 micron tip, 5 to 10 micron tip, you would get a reasonable trend in the AES response and also minimize the salt evaporation rate.
Fantastic. All right, Venky, have you tried any other metals and alloys to make sure the no peroxide one is more stable, or to help make the no peroxide one more stable?
Okay, yeah, I think it referred to that overall studies. So far, in that research, we only tried a tantalum titanium oxide as a test case to demonstrate the platform. However, there are plenty of research that were going on to minimize or to make a catalyst that is more overactive, that produces less intermediate peroxide. And there are another strategy wherein the hydrogen peroxide scavenger has been implemented into the catalyst layer or to minimize peroxide. But in our lab, we haven't tried anything on using ACCCM platform yet. But there are, as a fuel cell community itself, there are many research going on that aspect.
Excellent. All right, next one. This person says, "Hey, Venky, wonderful talk. Thank you. Just 2 questions. Can you explain what is SECCM bulk? And also, can you explain a little bit of why the impedance data does not correlate well with the surface microstructures?"
The SECCM bulk is what I mean is probably that you still use it theta capillary, but you immerse or use it in a way that SECM, wherein the entire surface is still exposed to the water. So you don't have the micro droplet based measurement. Rather, you control the diffusion of diffusion through the nanochannels at the tip. So that's why we are calling it still lattice bulk. Again, it helps in certain application where you can use a redox chemistry to monitor how the adsorption desorption behavior changes or the charge transfer kinetic changes. I think the second question is about impedance, why the impedance data does not correlate. It's again, we believe that is probably still to do with the micro humidity that changes that going on around the tip, because the impedance is very sensitive to that part of it. For example, any micro precipitation that forms around the tip typically could affect the impedance response. So that's one of the challenge we are still facing to control the or to stabilize the tip, the precipitate formation at the tip, especially when you use the salt solution. So I think that's one of the reasons it's not well correlated with the microstructures. Yeah, I will stop there.
Perfect. Yeah, great answer. Okay, can it be implemented inside a vacuum chamber for electron microscopy, for example, with liquid electrolyte with low vapor pressure?
That's an excellent question, at least from my side as well, because I used to work with a lot of vacuum instruments, particularly in ion soft landing technique. I did try it once to use the SECCM into the vacuum, but haven't made any measurement, but I tried once. It really depends on the tip diameter, and what I found out is that you need to have a really small tip diameter and long tapering so that it basically forms the force, the microcapillary force at the tip end does not pull is enough to counterbalance the vacuum force. And you probably can do the measurement in the high vacuum, but not the ultra high vacuum. That means the less than 5 torr, if your pressure is above -5 torr, it's fine, I would say. But that's an excellent question, at least for me.
Yeah, great question as well. All right, so All right, here's another good question. How does oil affect the polarization, as polarization may be affected by oil?
It really depends on the sample. There are some corrosion uh, sample, for example, like a steel or aluminum, does not really chemically react with the oil. In that case, the oil basically forms the layer around it, and when you have an aqueous ACCCM tip with the aqueous electrolyte tip end, you can really go into it and make a measurement. However, if your surface is reactive, then it's chemically reactive. It's going to right away start reacting and forming a product. We did try it with some catalyst or electrodes. It does not. We usually found out that there is some products that may be forming at the end. But there are some corrosion cases. It works really well.
Excellent. All right. Maybe I have time for just a few more questions here. Can you comment on the residues that are left on the sample surface due to evaporation?
Yes. So usually after you land the tip and make a measurement, the product leaves near on the surface, and you really need to understand what is the reaction you are doing. For example, in case of corrosion, you cannot do a very long measurement. That means because it will form a very thick product layer, and that sometimes the product can be picked up at the tip end and affects the next measurement. So you need to control the amount of product that's being formed on it, and that's something you know by the reaction. There is no other, I would say, at least with the SACCM, droplet SACCM, you cannot really control or remove the product, especially if it is a solid product. And the same case for the gas or other products as well.
Excellent. All right. I think in the interest of time, we'll just have one last question here, maybe a question looking forward. Venky, are there any developments in the field that you're especially looking forward to in the next 5 or so years?
I would love to see how this technique can be combined with the spectroscopy, especially in other modes of spectroscopy like Raman or IR, which really enables the characterization not only in electrochemistry but correlating that with the structural changes. There are plenty of advancement that was going on in this light spectroscopy. So I would love to see more developments on that aspect.
Fantastic. Yeah, definitely something to look forward to. All right. Well, Venky, thanks so much for sharing your insights today. It's really been a pleasure having you with us.
Thank you, Liam. Thank you for the opportunity today. And thank you, everyone, for listening and asking all these nice questions.
Yeah, definitely. Big thanks to the audience for participating. And we'd also like to thank the sponsor, of course, Harvard Bioscience and HECA. And in closing, we hope you enjoyed this Inside Scientific webinar, and we'll see you again next time. Have a great day, everyone.